First of all, thanks to the organizers. This has been a great workshop, and thanks for everyone who's here as well. It's been fun to see a lot of people I haven't seen in a long time and meet new people as well. So I'll be talking about Lévy flights on a periodic interval. Interval is key. It's a 1D problem, and I'll show kind of why I think that's still interesting for this particular case. And this is work that was done in collaboration with Sean Lawley after a short visit to the University of Pennsylvania, where I was doing a postdoc at the time. And so this is kind of an outline of what I'll talk about. I'll first describe briefly classical first hitting time problems, of which we've seen a few, and I think we'll see a few more still. Then I'll talk about Lévy flights and the fractional Laplacian. I'll describe this specific problem we looked at and talk about some of the interesting things that happen in this case. Okay, so classical first hitting time problems. One of the kind of fundamental questions is you have a small target in some bounded domain and you have a particle undergoing Brownian motion and you want to know how long it takes for you to hit the target. And so this has been studied a lot for many years now. There's still a lot of interesting problems within that space, a lot of variations on it. And I'm mostly interested in problems where targets are small, so they have some epsilon order radius, and epsilon is an asymptotically small parameter. And so how do you formulate this problem? I come from more of like PDEs and asymptotic analysis, so I'm dealing mainly with PDEs. So you define this first hitting time, which is the first time it takes for the Brownian particle to hit the boundary of the target. And then you take its expectation and it satisfies Poisson's equation with a Neumann boundary condition on the reflecting boundary. You kind of bounce back. And a homogeneous Dirichlet boundary condition on the boundary of the target. You've approached the target, you hit it, so the mean first passage time should be 0 there, right? And so, you can study this problem using asymptotics. And some of the results from the classical asymptotic analysis here is that if you think about this problem in 2 dimensions, you have this divergence of the mean first hitting time, and it diverges like a log of epsilon, whereas in dimension that should be a 3, not a 1. In dimension 3, it blows up like 1 over epsilon. Okay, so the mean first hitting time gets larger and larger as this target gets smaller and smaller. If you look at d equals 1, and this is not a typo, this is d equals 1, the mean first hitting time is just always order 1. And I think you can just write down what the solution is. It's a parabola, right? There's nothing interesting there. And one of the key things in understanding this behavior is understanding the corresponding Green's function for this problem. This is called a Neumann's Green's function. You have a Neumann boundary condition. You're solving for this function that it's a distribution. And then you impose this. You don't have to impose this specific form, but it just basically gets rid of an additive constant, right? And so I made a little table, just kind of summarizing 1D, 2D, and 3D. There's properties of the stochastic process, Brownian motion, properties of the Green's function, right? And by properties of the Green's function here, I'm thinking of its most like non-smooth behavior, right? So in 1D, it looks like a little hat. In 2D, it looks like a log. In 3D, it has this algebraic singularity. And then there's parallels then with how the mean first hitting time scales, right? It scales like order 1 because this thing goes to 0 and you just care about the constant term. It scales like log epsilon, 1 over epsilon. So there's a nice connection between these 3 things here, right? So we say these problems exhibit strong localized perturbations. And this is kind of what I was trained in during my PhD. Because you have these very small geometric defects in a domain and it has this very massive effect on the types of solutions you get, right? And so yeah, there's lots of literature on these types of problems. A lot of people in this audience have done a lot of work on this. There's still a lot of cool problems to work on. So what I was interested in during this project was looking at mean first hitting time problems for Lévy flights. And I'm going to do something a little bit odd. I'm mainly going to look at Lévy flights in 1 dimension, which in view of this guy here might not seem too interesting, but then we find that there's actually some interesting stuff that can happen in 1D. Okay, so what is a Lévy flight? Lévy flight, you can think of it as a continuous time random walk. You're waiting for like some exponentially distributed time, and then you take a jump, and the length of the jump that you take is coming from a distribution with a kind of a heavy tail. Okay, so it's got this algebraically decaying tail. and you introduce this parameter s. So this is in d dimensions. You introduce this parameter s, which is called the fractional order. And the smaller you make the fractional order, the kind of heavier the tail is, right? So as you decrease s, you're sampling from a jump length distribution that's got a heavier and heavier tail. So maybe you'll take bigger jumps more often. You can look at the generator for that stochastic process, and you get this thing called the fractional Laplacian, the principal value integral, and you have this kind of heavy tail thing appearing on the bottom. I like to think of this as an analog of doing like a finite difference discretization of a second derivative. If I do a second derivative finite discretization, I look at my two nearest neighbors, I subtract, I take the average. Lévy flight's doing the same, except you're now averaging over all of space, and that's a consequence of having these very long jumps from time to time. So you need to actually take into account the whole space. So this is another way of writing the fractional Laplacian. In fact, here I don't need the principal value. That gets rid of it. So it's an analog in some ways of what you would expect for generalizing the second order derivative. Okay, so motivation. We've had some discussion on anomalous diffusion earlier. Not everything is Brownian. And this is one example of an anomalous diffusion. There's some ideas that maybe Lévy flights might have something to do with foraging and biological function. I'm not an expert in that, but here's a picture of an albatross, and it looks like sometimes it takes these long kind of paths. And then there's also a description for Lévy flights in terms of bulk-mediated surface diffusion. You have particles on a membrane, they detach, they diffuse, and then they come back at another place. So now you have this point, like these jumps occurring on a membrane of some kind, right? And I like these problems because there's lots of cool mathematical structure for fractional Laplacians. It shares a lot of similarities with a lot of the theory that you get for the classical Laplacian, but it also has a lot of interesting quirks. Okay, so here's the problem we looked at, and I'll hopefully convince you it's interesting. We looked at a periodic 1D domain with a collection of targets inside of that domain. So imagine just looping this guy around, and you have these little targets of length 2 epsilon, and they're centered at a bunch of different points. And I want to figure out what the mean first hitting time to one of those targets is. If you do that, you write down an analog of the Poisson equation that you had for the classical case, except that there's some differences. Okay, number one, of course, there's now a fractional Laplacian because that's the generator, and number two, this condition here should look a little different compared to the classical case, right? I'm not specifying that v epsilon is 0 on the boundary of the targets. I specified 0 on the whole interval, right? And that's really boiling down to the fact that Lévy flights are going to be these kind of discontinuous processes. So it's actually kind of like a jump. So it's taking jumps. And so if I want to hit a target, I have to land in the target. There's no really discussion of hitting the boundary. That's never going to really happen. Okay, so Brownian motion in 1D, periodic boundaries. You look at a target and you want to calculate how long it'll take to hit that. You bound that with an order 1 quantity because Brownian motion is continuous. It's gonna hit it, right? I don't care how small I make that target. There's not going to be any scaling with epsilon where it blows up because I just need to cross a certain value, right? So that's not on its own too interesting. However, these Lévy flights are discontinuous, right? So that means that you have the opportunity to leap over your target. So if you look at another picture here, now I've decreased my fractional order. I'm walking around and I've leaped over, right? So I missed my target. I'm now on the other side, but I never hit it. So I don't have like this nice upper bound which says this mean first hitting time is always an order 1 quantity. There could be something interesting going on. And moreover, I showed you the heavy tail distribution, and it has this, algebraically decaying tail, and it's a longer and longer tail the smaller s is, which means that as I take a smaller value of s, I would expect there to be more leapovers, right? So now I'm leaping over multiple times before I finally land in the target. So now you would expect in this 1D problem, you might actually have a mean first hitting time that's diverging as epsilon goes to 0. Okay, and so that was kind of the motivation for looking at a 1D problem, which on its own, one might not think is too interesting. Okay, so I made another table here. And this time I'm going to plot or make entries involving the fractional order and properties of the Lévy flight. Okay, and so probabilists have studied these things in the past, of course, and you have like the analogs for Brownian motion. You have recurrence if S is greater than a half, neighborhood recurrence if S is equal to a half, and it's a transient process if S is less than a half. Okay, so we're starting to see some parallels with dimensions 1, 2, and 3 for classical first hitting time problems, and we want to see if we can leverage that. Well, what do I need in order to figure out my mean first hitting time? Well, we might guess based on these properties that it's going to be bounded up here, and then it's going to become unbounded here. But in order to really see that, we should figure out our fractional Green's function, right? So the fractional Green's function satisfies this equation, not too different from the one for the classical case. And you can rewrite the fractional Laplacian in periodic domains just spectrally. Instead of the Laplacian bringing down eigenvalues, it's eigenvalues to the power of s, right? Or 2s. And so you can write down a Fourier series of the Green's function. And I had been working on problems like this before in the context of spiky pattern formation. So I had nice expressions for this Green's function, where you basically just manipulate the sum and extract the least regular part, and then you have some more regular part, okay? And so out of that kind of calculation comes out this x to the 2s minus 1, which is hinting, right, at blow up versus no blow up. And if you look at s equals a half, you can pull out a logarithm, and then you have this regular part, which is more regular, right? Okay, so we have a Green's function, and this is what the singular part looks like. S is greater than a half. This is going to 0 as x goes to psi. This looks like log, and this blows up algebraically. So in grayed out text, I might say it's an order 1 quantity, it's log epsilon, and then it blows up algebraically. And so my table is complete, but really I should actually connect these two things together, right? So we can do that just using the method of matched asymptotic expansions. Okay, so the key idea for the method of matched asymptotic expansions, just before I go into those 3 steps, is you look at your outer region and how your solution behaves out there, where each target is just like a little point that you've removed. You look near each target, so you can kind of zoom in and formulate a different kind of core problem, and then you match the two things. The fact that this works out for the fractional Laplacian is a little bit surprising at first because this is a non-local operator. But to leading order, this still works out. You can show that the remaining terms are going to be small enough that you can basically ignore them. Okay, so first step, you zoom in on the ith target. The 1 over d on the right-hand side becomes 0. And so now you have to solve this problem. And this problem on its own, if you gave a PDE undergrad student this problem, hopefully maybe they would originally say the solution is 0 because it's a homogeneous problem, but of course we're in an unbounded domain, so you can just prescribe some kind of far field behavior and get non-trivial solutions. Okay, and so we did that in terms of what we called the fractional electrified disk problem, drawing analogies with the classical literature for mean first hitting times. I'll comment on the form of this. This equation is scaling invariant. I can take one solution multiplied by a constant, I get another solution, right? So that means my solution should really only be, I can only really specify a solution up to a multiplicative constant in front. Okay, so that's my BI there. And this guy here, I can then do some work and figure out expressions for it. And fortunately for all of us, I didn't write down what the actual solution is. I just wrote down its far field behavior. But you get these guys here in terms of like hypergeometric functions. Okay, and you can calculate it using these fractional Poisson kernels and stuff, and then you can ultimately relate it to special functions. And the key thing is it has this particular far field behavior. Again, not too surprising. We should expect logs, and we should expect these x to the 2s minus 1s. And these constants in front are things you calculate in terms of gamma functions. It's not a problem. Okay, so that's the electrified disk problem. That tells us the inner solution, right? Okay, so we have our inner solution. Step 2, we want to figure out our outer solution away from these targets. You've just removed little points from your periodic interval. There's some steps in between here, but it basically boils down to solving a problem with little delta functions at those points, right? So now you're thinking back to the Green's function, and fortunately, we already have the machinery for calculating that Green's function and understanding its singular structure. Okay, whereas the inner solution had multiplicative constant in front because it had the scaling invariance. Here we're solving fractional Laplace v equals something. I can always add a constant to v naught, so that gives me another degree of freedom. And so my solution looks like a linear combination of those Green's functions plus this chi up in front. Okay. So at this point, you don't know what the bi's are, you don't know what the chi's are, right? How do you figure them out? You do the final step of asymptotics, asymptotic matching, and you want to determine these by taking your inner solutions and your outer solutions and seeing where the inner solution goes as x goes to infinity and where the outer solution goes as you approach the locations where those delta functions are concentrated, right? So if you do that for each of the targets. There's n of them. So you do that for each of the targets, and that gives you then n equations describing how the bi's and the chi's and the bi's are all related to each other. Okay, there's one more equation though, right? That's only n, and that one more equation comes from a solvability condition, because if I go back to step 2, somehow, it seems so frozen. If you go back to step 2, if I integrate the right-hand side, use the spectral definition of this thing, I need the sum of these bi's to be 1 over c, right? But anyways, this allows us then to solve for the b's. It allows us to solve for the chi's. And in theory then, if we look at that right-hand side, we now have, right, if we look at this thing here, we now have an expression for the first hitting time in outer regions and then near each of the targets. So we've effectively solved the problem of finding an approximation to a solution, right? Okay. So what can we do with this? Well, we can now discuss the order of the mean first hitting time in those 3 scenarios and connect it exactly to the Green's functions, right? So if S is, okay, now it's working. If S is greater than a half, you can show from these linear system that all these quantities are going to be order 1. And so everything in here is order 1. The mean first hitting time is order 1. I'll also comment, this is order 1. This is order 1. So there's going to be lots of spatial variation throughout, right? If I go to S equals a half, you find that chi is order log epsilon, and the bi's are all order 1. Okay, so to leading order, this thing is actually kind of constant, right? And then this is more extreme if S is less than a half, because now chi is epsilon to the 2s minus 1. S is less than a half. This is blowing up. So you have this large algebraic term, and then you have these smaller spatially dependent terms. So we get the added little comment that in this case, the solution kind of looks spatially constant away from each target. Okay. And so then we can ungrade these out and we have a nice connection between those 3 things, right? Just for this one-dimensional problem. Okay. That's asymptotics. We don't have a rigorous statement for this, though I think there are ways. So we do numerical validation of this. I just want to comment on the difficulty of doing numerics for fractional problems. You got to discretize these non-local operators. You have all these really dense matrices, right? Also, you have small targets, so you probably want really refined meshes in order to capture the behavior near them. So you have very large, dense matrices that you then have to invert. That poses some numerical challenges. But you can do it, and there's some methods, and they just take a long time to solve, right? But it also leads to a linear system, so you might say that the asymptotics were pointless, but of course this is a much larger linear system, right? It's based on the discretization. So you need something much larger than 1 over epsilon number terms in order to get an accurate numerical solution. It's large, it's dense, it's kind of a headache. You can also deal with the fact that you're in a periodic domain, but you have a non-local operator, so there's periodic contributions, but you can sum these things up kind of analytically, which is nice. Okay, couple plots. Dashed curves are the asymptotics. No, dashed curves are the dashed curves here should be the numerics, and I think that the solid ones are the asymptotics. It doesn't matter, right? They're all really close to each other. The squares are from simulations of the actual stochastic process as well. And so we see good agreement. Mean first hitting time here for S 0.7, that's greater than a half. A lot of spatial variation everywhere. As I decrease epsilon by order of magnitude, not a lot of change in the height, right? It's an order one quantity. S is a half, you start to see more of a change in the order. Well, you start to see more growth as epsilon gets smaller and smaller. Agreement between asymptotics and numerics is still pretty good. S is 0.3. I just want to comment on here, right? Okay, we see the large increase in the mean first hitting time as epsilon goes to 0, but also it's almost spatially constant out here, right? So in this 1D problem, it's almost as if when you're away from a target, you're just kind of randomly distributing points in order to find a target, right? It kind of loses it somehow loses the spatial structure here, right? And that's because you're taking these very large jumps. Okay, I'll comment briefly on optimizing this mean first hitting time. So one question we could ask now that we have these asymptotics is, if we have some kind of distribution of targets, should we choose S close to 1 or should we choose S close to 0 in order to find the target as fast as possible? And so there's some kind of nuance in terms of how you set this problem up. We have this diffusivity in front. Diffusivity for these fractional problems is a relationship, kind of like for Brownian motion, right, of length scales to time scales for the jumps. But it's S dependent. It has different kinds of units for each S value. So it's kind of tricky to compare different Lévy flights for different S values, because these DSs are kind of, like, if you fix your DS, the characteristic length scales and spatial scales are changing each time. So instead we fix this L naught and this T naught. That allows the S now to vary. So you do that, and we considered this problem. It's the same problem as before, except we described how far apart the targets are, distance of 2L from each other, and they're each of length. The targets are each of length 2 epsilon L. And what we did then was consider the average mean first hitting time. So you average over all possible starting points, and you make this little function which will compare Lévy flights to Brownian motion, right? You're looking at TS over T1. And if you plot TS over T1, you get these curves. And they're functions of L naught over L. Okay? So for different values of L naught over L, I get a different curve as I change S. Now, what is L naught over L? L naught is the characteristic length scale for the Lévy flight. L is how far apart these targets are. If L naught over L is really small, the targets, from the perspective of this little creature doing a Lévy flight somehow, they're really far apart from each other, right? As L naught over L gets bigger and bigger, then it becomes more comparable. And so one thing we see is, right, if L naught over L is small, targets are really far apart from each other, it kind of looks like the minimum goes to S going to 0. It might be more beneficial to just kind of do these very long jumps. Whereas if they're kind of close to each other, then maybe you want to do Brownian motion, right? And so you can plot this S opt, the arg minimum of this thing here, and you get these nice kind of curves for different values of epsilon, describing how the optimal value of S changes based on the target density relative to the movement of this Lévy flight. Okay, so there's this nice kind of relationship there. So in conclusion, it's kind of surprising you can still do some matched asymptotics for these non-local problems, because it's, in spirit, it's kind of a local process, but you can still do it, at least to leading order. There's higher order effects that might play a role later on. And so it allows you to reduce this equation to this nice linear system of equations, and from there you can deduce nice properties. You can figure out all the qualitative properties from this linear system. And in particular, you see the scaling of the mean first hitting time, and you also see the spatial variation, how that changes for different S values. And then we also have, we can say something about a notion of optimal fractional order as well in terms of target density. Okay, and so with that, I'll conclude. This is the QR for this paper. There's other papers on Lévy flights, and this is in 2D, and Justin will talk about that later today. And then these are two kind of survey papers that I found really useful when I was learning about all this stuff. Yeah, and I'll be happy to take questions.
So is the limit as s goes to zero, you're just like just jumping on every time step? And is there some sort of careful way to take that limit? Because I would imagine there's like little very short intervals where you're moving and then you jump effectively. Is that
Yeah, the
and
S.
so is that like optimum really at s equals zero or like very, very close to zero?
It's a good question. I'm not entirely sure actually. When s going to zero, it kind of acts like the fractional Laplacian kind of acts like an identity operator. And so I think there's some more rigorous stuff people can do there. But if it is an identity operator, then your solution is 1 over d, kind of, right?
And so it's like you're just uniformly drawing a
Exactly.
point on the domain at each time step.
Yeah.
Okay,
Yeah. Yeah. Yeah.
cool. Thanks.
Two questions. First, is it possible to extend it to higher dimension? Do you see any way to
Yeah. So
difficulty for that? Or
there's difficulties. I think the switching behavior as the fractional order changes will mostly go away. But one of the later talks today will look at this problem as well in 2 dimensions. And then a lot of the challenges I think for higher dimensional cases are the trying to do numerical stuff for this and for validation. Just because you're dealing now with discretizations of higher dimensional spaces, and it's like these very large, very
do you
dense
expect
spaces.
that much asymptotic analysis?
Yeah, asymptotics should be pretty similar. Yeah, yeah.
Second, more technical question about this. You mentioned equivalence with respect to representation. Does it always holds?
Equivalence with respect.
You said when you wrote your Laplacian, fractional Laplacian, you said that you can use spectral
Oh
representation.
yeah, yeah.
Does it always hold?
That holds for certainly for a 1D interval with periodic boundary conditions.
Okay.
I think in a rectangular domain with periodic boundary condition, I believe it still also holds, but I might be wrong. This would be in here somewhere. Yeah. And if not in here, there's a survey paper by Batangelo, I want to say, that also covers this kind of thing. Yeah.
Thank you.
Yeah.
So there's a regime where the mean first pass type scales like epsilon, is it 2s minus 1?
2s minus 1. Yeah. 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 And as long as s is not a half, it's epsilon to 2s minus 1.
And then there's a regime where it's order 1.
Order 1 when s goes to
Between a half and 1, it's
when s is equal, yeah, when s is greater than a half, it's order 1 always, right? The Green's function is not singular. S is a half, it's log, and then s less than a half, algebraic explosion. Yeah. Yeah. And it gets worse as s goes towards 1 or towards 0, right? It becomes like 1 over epsilon. So it kind of looks exactly like 3D, at least from the scaling, but I think.
Other questions for Daniel? Okay, let's thank him again.